So, then I would suggest we continue. So now we have set our baseline straight. Let's have a look. Okay, what kind of attacks can we perform in an IPv6 network? There are of course several attack types. We have reconnaissance, we have network scanning, we have attacks on the local links, then we have routing headers, or in general fragmentation or extension header based attacks. What we will cover here mostly are the attacks on the local links. So we will see, okay, what kind of attacks can we do in regards to a neighbor discovery process, IPv6 route-related processes. MLD is part of the local link kind of attacks, but these kind of attacks will not be covered in this workshop. Will it be covered in the Chiron workshop, Raphael? MLD-based? Okay. So we will focus on the attacks on the local link and some remote DOS scenarios. So there are several tools available which can be used to perform these kind of attacks. The most famous one is the THC IPv6 tool suite, the Hacker's Choice from Mark Heuse, which can be downloaded on the URL. Then from Fernando Gont, he has developed the IPv6 toolkit to perform more or less the same attacks like with THC IPv6. The main difference between the two is IPv6 toolkit is better documented than the Hacker's Choice toolkit. But from an ease of use point of view, THC IPv6 is, from my point of view, the way to go. And then, of course, we have Chiron. Chiron is an advanced IPv6 attack toolkit or tool suite developed by Antonios Atlasis, a fellow researcher from Greece, of us, and you can download it here. And with Chiron, you can do all nasty things with fragmentation-based attacks, extension header, modification, and so on. It's not. You need a little bit of time to get used to all the knobs you can use. If you're interested in more advanced attack techniques, especially in use with Chiron, there is a workshop tomorrow for Chiron, which discusses several advanced attacks, which are then laid out with Chiron. So this is just a sample of a list of tools for the THC IPv6 toolkit to perform various kinds of attacks, which we will of course discuss in the course of this section. And our goal is we try to cover a wide range of IPv6 related attacks. Nothing new. These kind of attacks are very common and well known, but in order for you to get the big picture and of course be prepared when you start rolling out IPv6 in your environment. So let's start on the attacks on the local link. So there all these kind of attacks you can mainly split in two parts. The first part is all attacks related to the neighbor discovery process. So the typical ARP spoofing like we have in the IPv4 worlds. It's the same approach, and we have unfortunately the same problem in the IPv6 world. It's just called neighbor spoofing, but the goal is essentially the same. I want to spoof the entries in the neighbor cache of my victim so that I can get in a man-in-the-middle position to redirect traffic, IPv6 traffic in this case, to my client so that just I can read it, same as in the IPv4 world. And of course, you can interfere with the duplicate address detection, like you mentioned or asked before. Yeah, what is it when when the client is sending the packet to do the duplicate address detection? What happens when I just answer to it? Well, he tries to configure a new address, and at some point he will just stop, or the operating system will just stop to configure a new address, and then from an IPv6 point of view, it's just a denial of service because For the Microsoft space, here my client tries it 8 times, 4 or 9 times for the linked local address, and then he just gives up, and then he does not have any linked local address, and then of course he can't use IPv6 at all. Then of course attacks related with IPv6 router or the router advertisement process in general. So spoofing router advertisements, flooding router advertisements, which we will cover. And then, of course, there are some other variants of attacks, especially in the context of MLD, the multicast listener discovery. But as I already said, which will not be covered in this workshop. So then let's start with the attacks related with the neighbor discovery process. As I have already introduced the behavior functionality of duplicate address detection. As soon as the IPv6 stack gets initialized, the client configures a link local address, and the client has to make sure that this configured link local address is actually unique. All these DAD packets have a special characteristic. The source address here is always the unspecified address, represented as colon or double colon. And as we can see here, we see here 2 neighbor solicitation packets for a specific link local address. This is the actual link local address my client or this client wants to configure, but he has to make sure that this IPv6 address is unique. So he sends out a neighbor solicitation where his IPv6 address is in the neighbor solicitation packet. So when he receives an answer, he assumes, okay, there is already someone on the network who has this IPv6 address. Doesn't matter whether it's a link local address or a global unicast address. And so they assume, okay, it's already in use and need to configure another address. So then we have, of course, as we can see, after this process is done, the client tries to find the router. As we can see here, router solicitation. As we can see, there is a router, and he answers with a router advertisement, and to provide additional information for the clients. So, and the first thing we want to do. So I just pray to gods that the VM networking editor is working as desired, because that's most of the times a pain in the ass. So I'm currently just here in my in the Kali, and for the denial of service for the duplicate address detection inside the THC IPv6 tool suite, there is a tool called DOS new IP6. And when we just look here, this tool prevents new IPv6 interface to come up by sending answers to duplicate IP6 checks. This results in a DOS for new IPv6 devices. So for every device who already has configured an IPv6 address, it doesn't do anything. But every new device which tries to participate in the network will get DOSed because the tool is just answering the DAD packets. And let me just double check whether the configuration works. This looks good. So I'm just starting Wireshark, filtering to IPv6. So this looks pretty good so far. So then I will start the tool. So, and as you can see, it's pretty easy to use. You just say DOS new IP6 and then specify the interface on which it shall run. You just say ETH0, and now he listens to these neighbor solicitation packets for the duplicate address detection, and as soon as he will discover or sees one, he will respond to it. So we should Now, when I'm just, yeah, as you can see, what has happened, an IP address conflict for whatever reason. But what we can see, I just plugged in my new my Ethernet connection. So my client, of course, tries to configure a link local address. First, as we can see here, 43EE, that's the typical host part from my client. And of course, he tries to configure a global address based on the prefix switches in the router advertisements. So, and as you can see, he tries it a couple of times, but then he just stops. For the link local address, he has tried it once, 2, 3, 4, 6 times. So let's have a look what my interface configuration on the Ethernet network is saying. Do I have an IPv6 address or not? So, and that's the typical behavior. As you can see right now here on my HDA 0 interface, as you can see, I have a default router because I received a router advertisement, but the interface does not have a link local address and does, of course, not have any global unicast address because the attacker just, as you can see, just sending spoof packets, what then leads to my client giving up at some point. In this case, for the link local addresses, 2, 4, 6, he tried it 6 times with 6 different addresses, all in use, and then he just gave up. And so now this results in the a denial of service condition for the IPv6 connection, as my client does not have a link local address, and without a link local address, as you can imagine, there is not much IPv6 traffic or traffic you can initiate. And of course, the same applies to the global unicast addresses, and I just have to participate in the local network, and as soon as this is done, as you can see, pretty trivial, just say DOS new IP6 ETH0, and then he's just listening for these packets, and as soon as he sees such a packet, he will just spoof an answer, and then depending on the operating system which is in use, he will try it a couple of times to configure a new address, but at some point the client will give up, and then from an IPv6 point of view, we are kind of an undefined state, because the client does not have a link local address, he does not have a global unicast address, but he does have an IPv6 default gateway. So pretty trivial to do, and the consequences are denial of service for the IPv6 connection.
Would you recommend that enterprises that basically have unique MAC addresses just turn off DAD?
You could deactivate the duplicate address detection, but it would be what we call a deviation from default. The default behavior is that they do it. You can, of course, on client side, you can deactivate it, but this deviation from default always comes with an operational price tag, because you have to make sure over the whole life cycle of the system that this knob is deactivated, because it could be when you're installing a patch or a service pack or whatever, the DAD will get activated again. So you could theoretically do it, but at the price of it has an operational price tag, because you have to make sure that it stays deactivated over the whole life cycle. And to be fair, when you have access to the local link from an attacker's point of view, doing this, an attacker wouldn't do that. He would, of course, try to be a man in the middle to get traffic, or he would just flood the the network or the layer 2 domain with route advertisements, either flooding or fake route advertisements, so that you will have a fake default gateway. So these are, from my point of view, the type of attacks you should try to prevent them or protect against them. But this one, it's typically, I would say, not worth the hassle. But so if now one of your clients would connect to the network under the assumption that IPv6 is enabled, would not get a valid IPv6 configuration because your client would then at some point just stop generating an address. So would you mind just doing that for us to see it? So could you just, sorry? Yeah, so could you just unplug it and plug it in again, just for demonstration purposes, just okay. So your client tries to configure a link local address. So, but he stopped after the third one, when I see it correctly. So does your Ethernet connection now have a link local address? Just out of curiosity. Nope. Yeah, that is the expected behavior. And as we can see here, my Windows machine tried it 6 times. Your Mac, which version of Mac OS X are you running? The latest one. Just tries it. What happened now? Oh, no, it's just a screensaver, so everything's fine. Yeah, he just tried it 3 times, and then he just gave up and said, okay, the addresses I generated are already in use, so I just give up, and then you do not have any address. So as you can see, pretty simple to set up and to spoof, and which of course results in a denial of service. So I'll just stop that for a second so that you can participate in the network. So you have to unplug and replug it again. So hopefully your stack will now get an IPv6 address. But yeah, as you can see, these are the packets all with the colon here. These are all the packets the tool is listening to and just answering to it. As we can see here, no, we can't see it here, but as we have seen in the output, it just works as expected. So I have to do the same on my own because I want to have a proper IPv6 connection for my wired here. I'm just deactivating IPv6 and activating it again. So that should fix the issue. Let's just verify it very quickly. It looks good. I have a link local address, I have 2 global addresses, and I have my default gateway, so everything looks fine and dandy. So, but as you can see, pretty easy to do, pretty trivial. It's, yeah. So, yeah, sure. Yeah, that's the module inside the THC IPv6 toolsuite to do that. And from a complexity point of view, I would call it script kiddie-like, because as you can see, you just need a tool which is in the latest Kali or in Kali in general, and then you just say this and then the interface, and you're good to go. So pretty trivial to do, with a huge impact in case or for denial of service. So that's one approach to causing denial of service conditional by just sending these spoof neighbor solicitations for the duplicate address detection. A more interesting approach is, of course, to get a man-in-the-middle position, so that you can redirect traffic and read the traffic like we would do it in the IPv4 world. And as I've already explained, for the neighbor discovery process, we have the exchange of the neighbor solicitation and the neighbor advertisement packet. And as you can see, hopefully, here in the neighbor advertisement packet, what we can see here, the target address is the IPv6 address, and then we have a separate IPv6 option, which is the target link layer address, where the MAC address for this IPv6 address is stored. And this information gets stored in the local neighbor cache. So when I send a packet to this IP, I will be using this MAC address on layer 2. So, what can we do against that, or with that? We can use two different tools, or modules from the THC IPv6 toolkit. We could use the Parasite 6. It will redirect all local traffic. What just happens here, you just start the Parasite 6, and he will also listening to neighbor solicitation packets, and as soon as he receives the neighbor solicitation packet, he just spoofs the answer, the neighbor advertisement, to the requesting client, so that my MAC address gets stored in the neighbor cache for this specific target address, so that traffic distinct to one of these addresses is forwarded on layer 2 to me and not to the actual receiving client. So again, pretty simple to do. You just say here, okay, Parasite 6. What we can do here, we can of course loop this just to make sure that the entry in the neighbor cache stays the way we want it, so that our MAC address is stored in the neighbor cache entry and not the legitimate one. We can also try to inject the destination of the solicitation, so that we when we spoof a neighbor solicitation packet with a neighbor advertisement, the original destination will also get spoofed, so that I have a bidirectional man in the middle between a source and a given destination. And what you also see here, NS security bypass, we will discuss this in detail. There are mechanisms available on your typical access layer switches to prevent those kind of attacks. But unfortunately, these mechanisms can be circumvented by use of extension header or fragmentation. So, and if you want to perform this kind of attacks, and notice, whoa, okay, it does not work because these features are implemented on the switches. You can just here flip the F, H, or D switch to enforce fragmentation of the packet, so that the upper layer protocol information, so the layer 4 information, gets pushed into the second fragment. And as soon as that happens, the configured feature on the access layer switch does not work anymore, because he just looks at the first fragment, sees, okay, it's not related to the security function, and then he will let pass any subsequent fragments, which is part of one IPv6 packet. So what we do, we want, of course, to loop it. We want to also try inject the destination of the solicitation, and we use our interface ETH0. We can, of course, also include a fake MAC address, but we do not have to. If we do not specify the MAC address, he just takes the MAC address which is configured on my Ethernet connection. So, and doing that, again, he started listening, and as soon as he will see some neighbor solicitation packets, he will, of course, answer these packets and spoof them. So let's just give it a try. So I will just ping a non-existent IPv6 address in this segment, just to make sure that he will send out a neighbor solicitation. So, and as we can, what we can see here now is spoof packets for my link local address and the link local address of the router. He spoofed this to me for the router, and vice versa. He spoofed to the router that my link local address is now accessible over the attacker's MAC address. So you have to make sure, as you can see here, to get the man in the middle position and that the packets will get forwarded, you have to enable IPv6 routing. Otherwise, it's just a denial of service because the packets will be sent to you, but they won't get forwarded anymore. So, and you have to prevent sending out ICMP redirects. If you forget about that, your Linux machine will send a redirect to the client, informing them that they can reach a destination over another MAC address. To be fair, I think I haven't done it as of right now, but as you can see, he's sending actively the spoof packets as soon as he sees the neighbor solicitation packets, completely passively. So you do not have to do anything actively. You just have to be part of the local subnet. Just start this module, and then he will take care of the rest. So if it works as expected, we should now see this also in my local cache, in my ARP cache on my local client. So let's just double check. So where we have it. So as we can see, this is the MAC address of my EGA0 interface. So now have a look at my local neighbor cache. So, and what we can see now, as you can see, the internet address FE80::1, so my default gateway, resolves to this MAC address, which is the MAC address of my attacker. And this is the global unicast address of the router configured on the interface. As there wasn't any neighbor discovery related packets, this is the valid physical address of the router interface. But for the FE80::1, we see now that in the neighbor cache we have an association between the default router IP address and my IPv6 my MAC address. So if we compared it, I don't know if I can, looks, yeah, as we can see, 00, where do we have it here? 0C, 29E8, 13AB, and so on and so forth. So now every traffic destined for FE80::1 goes now on layer 2 to my machine, and so can be pretty easily be in a man-in-the-middle position for all inter-subnet traffic, as everything what the clients want to send over subnet boundaries will be addressed to me, because he has to address the local router. So pretty easy to do as well. As you can see, which is quite unfortunate, but it's that's the state of the implementation as of right now. This is one way to do it with the Parasite 6 module, but you can also send faked neighbor advertisement. And the beauty, in parentheses, of this approach is you can just send it to a special link local multicast address. Does anyone have an idea which link local multicast address might come in handy for that kind of ARP neighbor spoofing? Yeah, the all nodes. So what I can do, pretty simple. So, but I have to use another tool. That's the fake Advertise6. So what we can see here with the fake Advertise6, we can just send out spoofed neighbor advertisements. We can say, okay, how many times per second, or how many times in total, default is forever, in which interval should these packets be sent, the source MAC address to send from. Then we have a couple of options which we can set. In order to make this work, we have to make sure that the override flag is set so that an existing entry in the neighbor cache will get overwritten by the fake neighbor advertisement I am sending. But as we can see, this is the default behavior is that this flag is set. We can set the router flag to indicating, hey, okay, I'm a router. As we can see, that's in the default not set. And the typical knobs to evade the first stop security features on the switches. And on the as target address, I can just use the FF02::1. So I can spoof the whole subnet with just one periodically sent packet, and every client on the link will get this packet and will, of course, process it and adjust the entry in the neighbor cache, which is quite unfortunate. Even the router will, of course, receive this neighbor advertisement. But one could think, okay, if the router sees a neighbor advertisement where his address with a different MAC address is listed, that he may tries to prevent it. In the IPv4 world, at least in the Cisco space, if you try to do ARP spoofing with the broadcast address, the Cisco router will immediately send out a gratuitous ARP packet to ensure that the correct ARP information is stored on the client. Unfortunately, the Cisco router is not doing this for IPv6. So even though the router receives the neighbor advertisement, which is sent to the link local all nodes address, he could potentially send out the neighbor advertisement, but he doesn't do it, which is quite unfortunate. Maybe Cisco will do it sometime in the future, but I just tested it 2 weeks ago, and I wrote a small blog post about it. So in the IPv4 world, he sends a gratuitous ARP. In the IPv6 world, he just does nothing. And what we want to do, we want to set the override flag. We want to set the R flag because we want to be a router. So then we say, okay, count forever. We want to send these packets every 2 seconds. And then we want to interface IPv. We want this address, and oh, just a second, that was not what I wanted to do, but it works in any case. Yeah, well done. That's what I wanted to do, sorry. Yeah, what we can see here now is that the link local address FE80::1 is sending out neighbor advertisements on the local link. Just a second, I just want to deactivate the automatic scrolling. Here, this one. Yeah, so what we can see here now, my client or the attacker is sending the neighbor advertisements. Why are you scrolling? The neighbor advertisements, but when we look here on the Ethernet address, the source address is, of course, the MAC address of my client or the attacker. The destination MAC address is the MAC address which corresponds to the linked local all nodes multicast address. As we can see here, we send it to the all nodes IPv6 address, and here in the ICMPv6 neighbor advertisement, what we see here is the target link layer address, which is of course my MAC address again. And when we have made sure that the O flag is set, then an existing entry in the neighbor cache of the victims will get overwritten with the information which are stored in this neighbor advertisement. So, and we should see that now again, because I stopped the other one. Give me just a second, just to make sure we are in a clean state. Yeah, what we at least now see here, I unplugged my cable, but for the FE80 colon 1, now there's also my MAC address associated. So same setup as with the Parasite 6 module, but in this case I just can send it to the linked local all nodes multicast address, and then I can spoof, for example, the default gateway for the whole subnet. I do not have to listen to these neighbor solicitations. I just send it out to the all nodes, and nothing happens. I mean, we can actually have a quick look on the switch router here in the front, which is the which is acting as the IPv6 router. So, is it readable with this font? Yeah, okay. So, if we have a look at the logs, the only thing what we can see is link up, link down events. I connected directly to the console, so I don't have to activate the terminal monitor. And I'm actively sending these packets, but as you can see, the Cisco just doesn't care about it. So there's no indication that this is happening. One thing I could do, and I have tried, what you could do, you could well, I tried to activate this logging mechanism just to evaluate, okay, does it say anything on the console or in the log files when this login is enabled? He does not. So if you do not have any IPv6 first hop security features implemented on your access layer switch, you won't notice it on a router or device that there is someone spoofing actively the address. So when we're looking here in the neighbor cache, of course, he is not listing himself in the neighbor cache, which is a little bit different than in the IPv4 world. In the IPv4 world, in the ARP cache, he always lists himself, but not in the neighbor cache. So as we can see here, he has this link local address, and I assume that the router, from a logical point of view, says, okay, I mean, I received these spoofed neighbor advertisements with the link local address I have already configured, but he will still use his MAC address for his address. So there is some kind of logic implemented, but only for himself and not for any other participants on the network. So again, pretty easy to implement all these kind of attacks in regards to neighbor discovery, as we have seen. Pretty trivial to do, nothing fancy, nothing complex. Just download the tool, use the specific module, and then you're good to go. And then, of course, you can do whatever you like with the traffic you receive. Yeah, that's just what we have already done. Send spoof neighbor solicitation to find MAC address, sniff IPv6 traffic, and so on and so forth, just to perform a traditional man-in-the-middle attack on the local link. I mean, you could also use Scapy. I mean, you can do everything with Scapy. It's a little bit more complex for constructing the packets, but you can do it with Scapy. You can do it with the IPv6 toolkit. You can do it with THC. So every IPv6 attack toolkit has a feature to do the man-in-the-middle based attacks on the local link. Yeah, and as I already said, you have to make sure to enable IPv6 forwarding, otherwise you will just DOS the targets, and that's most likely not your goal because you want to be transparently between two entities to sniff the traffic of those. Sorry. And so you need to make sure that IPv6 forwarding is enabled. So that's about it for the neighbor, or for the most relevant neighbor discovery related attacks. So let's continue with the router-based attacks. So the general problem is, as we already discussed, the router advertisements are part of the auto-configuration approach and are fundamental part of the IPv6 DNA. And by default, the local link is regarded trustworthy. So as we have already seen, we could easily launch all these attacks regarding neighbor discovery, and the same, unfortunately, applies for the router advertisement-based attacks. So what could happen? Two scenarios. Let's say, for example, one machine in your network accidentally starts to sending router advertisements. Could be a virtual machine, could be a Soho device some of your users brought into your network and just plugged it into the network. It could be, at least in the past, a Windows system where internet connection sharing gets enabled, because in the early days, the Microsoft Windows operating systems started to send neighbor router advertisements as soon as internet connection sharing was activated. This has since then been fixed by Microsoft. They have provided a patch that they won't send any router advertisements when ICS is enabled. Or the other scenario is that an attacker interferes with the router discovery approach. So that is by either denial of service the target by just sending many bogus router advertisements, or of course traffic redirection by spoofed router advertisements. So when I'm just sending router advertisement, my client will of course install this link local address as an additional default router, which is quite not very intuitive, because the name default router implies, okay, I have one. And typically in an IPv4 world, you have one default router configured. In IPv6, that's not necessarily the case. You can have multiple default routers configured on your interface, and to evaluate which of these default routers is actually used, you have to have a look into the local routing table of your operating system. So the first thing we can do, we can just get information about the current router advertisements which were sent. No, I want to go here. Yes. So just dump router 6. So, and then we get the information about the route advertisement for the legitimate client. As we can see here, we have a hop count, we have our flags, no M flag, no O flag, and so on. And we have here our prefix information. And what I can do now is, the first thing I want to do is just sending fake router advertisements so that my client will install a second default router. So what I will do, we have a separate module for this. It's called fake router 26. Pretty simple. As well, as you can see, it has a little bit of more knobs because you can adjust every parameter in the router advertisements, but we want to keep it simple. What we want to do now is we want to do fake router 6. We want to, let me just check. We want to send it with a specific prefix. Let's just do 2001 db8 dead beef so that we can easily identify it. And then we should be good to go. Yes. So now the client, the attacker is just sending periodically these fake router advertisements, as we can see here. And when we are filtering here for these router advertisements, Gesundheit. What we can see here, which one? This is the legitimate one. No. So this one is the one sent from the from my virtual machine. And having a look at this, at the content of the router advertisement. I hate those beamers with low resolution. What we can see now here is that the specified prefix is also included. So as a result, my client should now have 2 additional IPv6 addresses based on the prefix information, which are stored here in this router advertisement. Let's have a look. And your client should as well, as long as you are connected to the network. Yes, this looks good. As we can see here, I do have now 4 IPv6 addresses in total, 2 from the legitimate router and 2 from the spoofed or faked router advertisements. And as you can see here, I now have an additional IPv6 default gateway. So, and now I have in total 2, but in order to evaluate, okay, which of these default gateways will the client use, you can tell it from this output. One could assume, okay, this one is listed first, so it will use this. No, that's not the case. You can tell by the ordering of the default routers here which of the routers he will actually use as a default gateway. So in order to do that, you have to have a look at the local routing table on the client. And what we can see here now is that we have 2 default routes. Both are pointing to, just excuse me, ignore this one. As you can see here, we have an interface identifier. This is the default route which I got from my Wi-Fi connection for the conference network. The number 15 is my Ethernet connection, as you can see here. Number 15 is my Ethernet connection, correct. So, but what we see here now for the default route for my Ethernet connection, as we can see here, we have 2 separate gateways. But looking here at the metric is different. And from a routing perspective, the lower the metric, the better. So in this case, or in this scenario, if my client would need to send packets to a different IPv6 prefix, he would not use the legitimate router, but the attacker, because he just looks in the routing table, says, okay, I have 2 default routes which are pointing to the Ethernet interface, but this one has a lower metric, and of course will then be used for every inter-prefix traffic. So now you could ask yourself, okay, why is that the case? Why does my client prefer the router advertisements from the attacker and not from the legitimate client? Well, that's pretty simple. Inside the router advertisements, you have, where do we have it? here we have a preference value. The preference value just determines when a client receives route advertisements from different sources, which of these sources should he prefer. And for this decision, he looks into the router preference to decide which route advertisement he should prefer. And the attacker is, of course, setting the router preference to high. The router preference can have three values: low, medium, and high. Medium is the default one, and the attacker has set it to high. And the legitimate router advertisements, as you can see here, are configured as medium, which then leads exactly to this case that the clients are preferring the route, the default route from the attacker and not from the legitimate client. I mean, I can, of course, adjust the router preference on the router pretty easily. So, and just also set the router preference to high, just to make sure that the preference from a legitimate client's router is also set to high. What we see here, that we now get some kind of information that there is another router on the network on VLAN 10 with some conflicting neighbor discovery settings. So this is an indication that there is another entity in your local network, in this case VLAN 10, which is sending out router advertisements. So looking back at Wireshark, what we see now is that both are sending their router advertisements with a preference of high. So here the spoofed one, nothing changed, and now here the legitimate one, also with high. Going back to the routing table, to the local, let's see how this changed the entries. And as we can see now, again, two default routes, but now they both have the same metric, which is quite unfortunate. Because at least in the Windows space, what does Windows do here? Windows is doing a per packet load sharing. So one packet to the legitimate router, one packet to the fake router. So at least half of the packets would arrive on the attacker. But when you have such a conditioner, do not expect that IPv6 is working as desired. And that's the only thing you can do from a router perspective, so making sure that the router preference is always set to high, just to make sure when someone introduces a device into your network which accidentally sends out router advertisement, they are typically sent out with a medium preference, and just to make sure that this router is not tampering with your valid IPv6 configuration. You should just make sure, with no exception, that on every interface that the router preference will be set or is set to high without exception. Sure.
There are some router models where you can exactly specify that, let's say you have 20 ports.
Yeah.
And you know that the router is on one port and only on that port.
Yeah. Yes, that's possible. That's well, I mean, for the typical enterprise-based models, Cisco, HP, they all support these kind of functionality. We will discuss that shortly. So you can theoretically do that, but as I've already said, they work as expected, but you can unfortunately circumvent all these features when you just fragment, for example, your spoofed router advertisement. So what you want to achieve is you want to fragment the router advertisement so that the upper layer protocol information, so the information that this packet is a router advertisement, will get pushed to the second fragment. And at least in the Cisco space, the Cisco device, when this feature is activated, will just look at the first fragment, sees, hey, that's not a router advertisement, and will let every other fragments pass without further inspection. The problem is, I mean, theoretically it could be done on a switch, but it would be pretty expensive CPU-wise, because the switch had to store all fragments for the packet, has to reassemble it, has to make the decision, has to fragment it again, because in an IPv6 world, the switch or the router does not do or must not reassemble the packet. So he has to reassemble it, make the decision, fragment it again, and forward it to the actual destination. So theoretically it could be done, but it would be pretty expensive CPU and resource-wise. So, or that's the fake one. Oh, come on. Yes. Okay, then I'll just shoot him in the head. Please wait. Please wait. So that's just the fake router scenario. What you can also do is you can just flood the network with router advertisements, which, depending on the operating system, might cause a huge CPU load during you perform this kind of attack. And there was a vulnerability, especially in Microsoft operating systems, which was discovered back in 2010, when you're just sending a huge amount of router advertisements, then eventually all resources in the kernel from the Microsoft operating system just get exhausted, and the machine is running on 100% CPU load forever, even if you stop the attack. And it took Microsoft quite a while until they fixed it, more or less, because they said, hey, that's not a vulnerability, that's expected IPv6 behavior. And I think it was in 2013 they released a patch, but they didn't say it was a security patch. It was named an IPv6 readiness update, where they just, what have they done? Yeah, they limited the amount of IPv6 address on a given interface to 100. Before that, it was just unlimited. So with this patch installed, at least in the Microsoft environment, during the attack, you will see an increased CPU load. But as soon as the attack stops, at least the CPU load goes down. Still, your client will have 100 IPv6 addresses configured on the interface, and do not expect that IPv6 behaves like it should when the client has 100 addresses on the interface. Yeah, we already discussed this, fake router 2.6. And this is the CVE, as you can see, from 2010. Protocol implementation on these operating systems allows remote attackers to cause denial of service by sending many router advertisement messages with different source addresses. And this was the initial behavior of Microsoft-based systems. We have tested this back in 2010 for that was at that time a 2008 server, which was actually, that was the new laptop of my boss, and we just got it new, installed it, and then we said, okay, let's just try it. Quite a powerful machine, 6 years ago, 8 CPU cores, 16 gig of RAM, so not a slow one. So we performed the attack for, I don't know, 30, 40 seconds, then just stopped and tried to have a look, okay, can be anything done with the operating system. And as we can see, the CPU load spiked to 100% and stayed there for the whole night, because we went out after we finished it, came back the next morning to see, okay, is the CPU load still at 100%, and it still was. So, and we were able to open the task manager, and the task manager was under the assumption that he does not have any active network interfaces. So pretty trivial to do, and it's a complete denial of service for the whole box, which is of course quite unfortunate. Let me just.
You said that Microsoft has
Well, kind of. So my box here has, of course, my Windows 7 box has this patch, this IPv6 readiness update installed. So what we do now is we just start sending many bogus router advertisements. Just be aware that I'm, of course, paying in virtualization tax, even though in this virtual machine, the sending of the router advertisement isn't that fast. When you're doing it natively, you can push up to 120,000 route advertisements per second with a gigabit interface when you're doing it natively. So, and for this, we are just using the flood router 2.6 module. It's even easier to use. What we can do is we just send out many bogus route advertisements, and we see here we also have some configuration knobs to bypass specific security features we will discuss in a minute. So we're just doing a plain for just say. So on every dot printed here are 1,000 packets. I mean, I'm also DOSing my host machine where the virtual machine is running, so the virtual machine isn't that fast to send these neighbor advertisements, and hopefully I haven't shot myself in the foot. I should not, but as you can see, you see that there isn't anything moving anymore. So it would have been smarter to deactivate IPv6 on my interface here. So, but what you can see, it's barely usable anymore. But as soon as hopefully I can stop it. Otherwise, I just. Yeah, that wasn't a good idea from mine, but in any case, we will get it fixed. But as you have seen, nope. As soon as the attack starts, the machine became pretty unusable, but only during the attack. When the attack stops, the machine will be usable again, but will still have 100 IPv6 addresses configured on the interface. Before this readiness update, the machine would completely block into this state and would only be recoverable by rebooting the system. So, and this is the aforementioned IPv6 readiness update. So, how have they fixed this? Issue 2, if you use many IPv6 addresses and routes, the kernel memory is exhausted and CPU usage reaches 100%. This update limits the number of advertised prefixes and routes that each interface can process to 100. Well, they could realistically have cut it down to 10, it would still be sufficient, but they decided to do it for 100. So under the assumption that you have installed this update, during the attack, the machine is barely usable, but quickly recovers after the attack ends. Still, as I said, you have 100 addresses on the interface, IPv6 addresses, and it depends on your policy on the WSUS, the update server from Microsoft, because this is neither a critical nor an important one. It's just a recommended one. So if you're not installing recommended updates in your enterprise networks, you may have not this update installed. So you should make sure that you're also installing recommended updates. So what can be done against Dhcpv6? Well, to make it short, it's pretty much the same as in the IPv4 world. The same risk or problems we have in the IPv4 world are now in the IPv6 world. It's a little bit less because we cannot distribute default routes for over Dhcpv6. but in general, the overall risk is pretty much the same as in IPv4, and therefore, the same mitigation techniques will apply when you have implemented DHCP snooping in your IPv4 network. You will most likely implement Dhcpv6 Card for your IPv6 deployment under the assumption that your hardware is, of course, supporting it. So these are pretty much the attacks on the local link. Now, let's have a look. Okay, that all sounds really bad, but what can we do about it for these local link attacks? As I already said, there are a couple of features which can be implemented on your typical access layer switch when he is supporting the IPv6 first hop security features. So, as we have seen, we cannot rely on protocol properties to protect our IPv6 network, so we have to make use of these features on the switches. But it's actually pretty hard because the features are there. They just can unfortunately be easily circumvented, how I will show you in a minute. So, one thing you could do for all these router advertisements based attacks, you could, of course, configure locally on every host that router advertisement will not get processed on the host. So even if it receives a router advertisement, he just does not process the packet. Well, for server segments, that might be feasible. Still, it's a deviation from default, same as with DAD. Yes, you can do it, but you have to make sure that this configuration knob is deactivated over the whole life cycle of the system. So you can do it for server segments. For client segments, forget it, because otherwise you would have to configure the default gateway on all clients manually, and that's just not operational feasible. So that may be a mechanism for server segments, but not for client segments. And when you are doing that, always remember it's a deviation from default, what we call it, and it always requires operational expenses. Yeah, and it might not scale because your IPv6 network might have 50 systems today, but what about tomorrow? And of course, it adds complexity. But it can be done on all operating systems. We won't discuss this in detail. It's just some slides where the configuration item is listed, how to deactivate it. So, but at the end of the day, what we will use when we are trying to protect us against all these kinds of attacks, as I said, we have to rely on security features which are implemented on the switches, and Cisco was the first vendor who implemented such kinds of features. Cisco calls them first hop or IPv6 first hop security. So on your first hop, your switch, to implement specific features to prevent some kind of attacks. So these kind of features Cisco implement then in a phased approach, divided into 3 phases, 1, 2, and 3, where in every phase new features were implemented into the boxes. And so the first phase is dating back in summer 2010, and Cisco introduced IPv6 based ACLs and RA Guard. RA Guard is functionality, as the name implies, that you can use to prevent the router advertisement-based attacks. It implements more or less an isolation principle, similar to other layer 2 protection mechanisms. Basic principle is really simple. So when I have my switch, and I have my router. I just configure router rguard here, where clients are connected, and when the client is sending a router advertisement, it just gets filtered by the switch. Pretty simple, pretty easy to implement, and it works more or less like a stateless filter, which just filters IPv6 type 134 in this case. Pretty easy to configure as well. It's just one configuration knob here IPv6 in the rguard, and then you're good to go. This is called the light variant. You could also use the sophisticated one, where you can define in a policy which parameters are accepted inside a router advertisement. But from our point of view, this light configuration should be enough for most deployments. So then we had phase 2, where Cisco implemented Dhcpv6 Card. So and NDP snooping is the equivalent to DHCP snooping and dynamic ARP inspection in the IPv6 in the IPv4 world, so that you can prevent the problems with rogue Dhcpv6 servers and the neighbor spoofing in the IPv6 world. Implemented them since 2012, now 4 years ago. Then we have, of course, Dhcpv6 Card. Similar functionality like DHCP snooping in the IPv4 world, blocks reply and advertisement messages that originates from malicious DHCP servers or attackers. So same configuration approach. I just configure Dhcpv6 Card here on these interfaces, and when the client sends a DHCP v6 server packet, the packet will just get filtered. So, but you could also configure a sophisticated policy where you can explicitly define what is allowed in the DHCPv6 packet for the prefix, who is allowed to send these packets, and so on. Here the same, you can just use the light variant, which is just applied to the interface, or you can use the policy-based variant where you have just more configuration knobs. But from our perspective, using the light variant for RA guard and Dhcpv6 guard is for most deployments sufficient, as you just want to prevent that some unauthorized entity is allowed to send a router advertisement and or Dhcpv6 server packets. So, but for the NDP snooping, the switch, of course, has to store a local table. So when he sees a spoofed neighbor advertisement packet, so that the switch can make the decision, okay, is this a legitimate neighbor advertisement or not? So, and in this case, as you can see here, the switch builds a so-called security binding table, where he stores all information he has learned. As you can see here, for example, he has learned some addresses over the neighbor discovery protocol, IPv6 address associated with the MAC address and on which interface. And if I now try to send a spoofed neighbor advertisement, for example, this address, the switch will block the spoof neighbor advertisement, because we will check the neighbor advertisement against the entries here in this neighbor security binding table, and if they do not match, the switch just discards the packet. Yeah, and this is achieved with the snooping feature, and the snooping feature is the baseline for a lot of, or quite a lot of these first hop security features. So this is it again, the security binding table. And here's just, at least for a Cisco space, if you need to deploy IPv6 and wondering, okay, which version and which platform do I need to use for to use all these these features. Here's just a nice summary. As we can see here, at least for the typical access layer switches which you are using, 2K, 3K, or 3850. It's already implemented, starting with 1502 SE. And but for the Nexus platforms, 3K, 5K, and so on, here it is listed as NXOS 7.2. In the meanwhile, they have postponed it to NXOS 8.0. So before that, you won't see any first-hop security features in NXOS-based systems. Well, using these features, you should consider it, but of course you also need to know about the limitations of these features. I mean, all these features, when you are implementing them, and we are just sending plain route advertisements or plain DHCPv6 packets or plain neighbor advertisements, all these features work as expected. But the problem is that all these features can be circumvented by... Am I already over time? Oh yes, I am. But we will be finished in a couple of minutes. Sorry for that, that I prevent you from getting something to eat. But lunch will be downstairs, so there will be enough for everyone. So, but the problem is that all these features can be used or can be circumvented by the clever use of extension header and or fragmentation. So that means, I don't know if you can see it. No, you cannot. The first packet here is a fragment, the first fragment of an route advertisement in this case, and the second packet is the actual route advertisement. What is done, or what was done, as we can see here, this router advertisement packet contains or consists of two IPv6 fragments. The first fragment is 1232 bytes, and the second one is 40 bytes. What happened here? The router advertisement packet gets fragmented, so that the, as I already said, the upper layer protocol information, so that this packet is an router advertisement, will get pushed to the second fragment, and the switch only checks the first fragment and let every other subsequent fragment pass for this packet. And how is this achieved? Pretty simple. To achieve the fragmentation, what we can see here, we are just using a destination optional header and just padding it until fragmentation occurs, so that the upper layer protocol information, so the ICMPv6 header, is in the second fragment. And that's the general idea, or the general approach to circumvent all those features. You can, of course, also do quite a lot of other stuff with extension header, which Raphael and Antonius will most likely cover in their Chiron advanced workshop. But this is one application where extension header have gone bad from a security point of view, as they are used here to circumvent all these features. So that's pretty unfortunate. The only real resolution to this problem is this RFC 6980, which was specified by Fernando Gont and released in August 2013. This RFC does not allow the fragmentation of any neighbor discovery related packets. So fragmentation for these kind of packets is prohibited as long as the host stack implements this RFC, so that even though when I'm sending a fragmented router advertisement, that the client does not process this and just discards it. But the problem is in Linux-based systems it's already implemented. Up until now, I don't think that it's implemented in Windows, because I also asked the Microsoft employee over Twitter, hey, what's about RFC 6106 and 6980, but I haven't got any answers. So if they would have implemented it, I would assume he would say, yes, we have it, but I don't think that's the case. So, and that's the, from my perspective, the only real way to resolve these issues, that all hosts implement this RFC so that the fragmentation of all neighbor discovery related packets is not possible anymore, or more precisely, it is possible, but the receiving clients will just not process the packet. But we will see how long it takes Microsoft to implement this RFC. And when this RFC is implemented, these features will work more or less reliably, besides maybe some implementation bugs in your enterprise network. And that's our general recommendation as well. When you're thinking about deploying IPv6, you should at least have RA guard in the light variant and Dhcpv6 guards. You should make sure that these both of these mechanisms are supported on your access layer platforms, and use them or configure them properly. Another approach would be to work with port-based ACLs. Yes, would address the issue, but working with port-based ACLs also has an operational price tag, as you would have to apply this access list on any user-facing port. So would work, but operationally expensive. So, conclusion. So, as we have seen, different attack surface than in the IPv4 world, and lots of old and new attacks, just because of different protocol behavior. And even if you now think, yeah, okay, I'm not using IPv6, everything's fine, I'm not vulnerable to it. Well, unfortunately, that's not the case. As soon as your IPv6 stack is enabled, even though you're not using it in any form, you are vulnerable to all these kind of attacks, especially the router advertisement-based attacks. And IPv6 is enabled by default on all modern operating systems. And as we have seen, performing these attacks is pretty simple. Defending against them is actually, as of right now, pretty hard due to potential hardware limitations on your access layer switches, and paired with the easy circumvention of those first hop security features. Yeah, and if you're a vendor or something like that, or if you need to implement an IPv6 stack, please do us all a favor and implement RFC 6980. So, I'm already over time. Hope that's fine for you, but lunch will be there. So, any questions? So then, thank you very much for your attention. I mean, I will be around the whole week, so if you want to discuss anything or ask anything, just feel free to approach me. If there aren't any questions, thank you very much for your attention. I hope you enjoy the rest of the IPv6 Security Summit and or Troopers, and then have a nice lunch.